The third example, I am considering a discrete time Markov chain. Obviously, it is a time homogeneous discrete time Markov chain with the one step transition probability matrix satisfies the additional condition, that is the column sum, that is also going to be 1. Obviously, the stochastic matrix means the row sums are going to be 1, and here I am making an additional condition along with the row sum, the column sum is also going to be 1 for a finite Markov chain. In this model, in this situation, this stochastic matrix is going to be called it as a doubly stochastic matrix. That means, it is a stochastic matrix, that means each entities are lies between 0 to 1 and row sum is going to be 1. Along with the row sum, the column sum is also going to be 1. Then that matrix is going to be called it as a doubly stochastic matrix. If you have a discrete time Markov chain with the finite and a doubly stochastic matrix, and also it is irreducible, I am making additional condition. If it is a finite irreducible with the probability one step transition probability matrix is a doubly stochastic matrix, then the stationary probabilities exist, as well as that stationary probabilities are going to be a uniformly distributed, that is that values are 1 divided by n, where n is the number of states of the discrete time Markov chain. To get this result, you can use all the previous results also. It is a irreducible Markov chain, therefore, and also it is a finite. So, for a finite irreducible Markov chain, all the states are going to be a positive recurrent. You can use the previous result, only the aperiodicity is missing, but since it is a doubly stochastic matrix, that aperiodicity is taken care. Therefore, the stationary probabilities exist. Now, if you compute the stationary probabilities for a doubly stochastic matrix situation, then the pi is equal to pi p if you solve with the summation of pi a is equal to 1. Since the matrix is going to be a doubly stochastic, that means its column sums are going to be 1. Therefore, it is going to be boils down, or the simplification is boils down to the state probabilities are going to be 1 divided by n. I am not going to give the derivation for that, that can be worked out. Example, that is example 4. You consider a two state model. The system is going from the state 0 to 1 in one step, that probability is 1, and the system is going from the state 1 to 0, that probability is also 1. Therefore, the P matrix one step transition probability matrix 0 to 0 is 0, 0 to 1 that is 1, 1 to 0 that probability is 1, and 1 to 1 that is 0. So, this is a one step transition probability matrix, and if you see that this is a finite state model, irreducible, it is not aperiodic because there is no self loop. So, if you find out the periodicity for the state 0, the greatest common divisor of system starting from the state 0 to coming back to 0, in how many steps you find out the greatest common divisor of that, and since it can come back in 2 steps or 4 steps and so on, therefore, the greatest common divisor is 2. Similarly, since it is a finite state model, if one state is of periodicity, then all other states also going to be a same periodicity as long as it is a irreducible. Therefore, the periodicity for the state 1, that is also going to be 2, or you can compute separately coming back to the state 1, starting from the state 1, that is going to be either 2 steps or 4 steps or 6 steps and so on, that therefore, the greatest common divisor is 2. Since it is a irreducible model, all the states are going to be of the same type. Since it is a finite, one is going to be a positive recurrent, therefore, both the states are going to be a positive recurrent. and a periodicity 2 and irreducible. Note that the example which I have formulated, the column sum is also 1, therefore, it is a doubly stochastic matrix. Therefore, you can use the previous result, the example which I have given, finite, irreducible, doubly stochastic. Therefore, the stationary distribution exists. So, if you solve pi is equal to pi p with the summation, pi is going to be 1, where pi is nothing but pi naught pi 1 vector. So, if you solve pi is equal to pi p with the summation of pi a is equal to 1, you will get pi naught pi 1, that is same as 1 by 2 1 by 2. So, this is the stationary distribution that exists, and that value is a state probability, stationary state probabilities are going to be 1 by 2 1 by 2. That means, in a longer run the system will be in the state 0 or 1 with the probability of. Whereas, if you try to find out the limiting state probabilities or limiting distribution, that means the limit n tends to infinity p of n, that means find out the n step transition probability matrix, then you make a n tends to infinity. This does not exist for this model. If you see the result which I have given, the limiting distribution, it is going to be exist and unique and so on. There I have made there I have not discussed the periodicity, there I have made it a aperiodic. So, here it is a period 2 model. So, whenever you have a irreducible positive recurrent state, if the periodicity is not 1, that means it is not a periodic model, there is a possibility the limiting distribution will not exist, but still the stationary distribution exists. So, this is an example in which the limiting distribution does not exist, whereas the stationary distributions exist. But if the model is irreducible, aperiodic, positive recurrent, then the limiting distributions exist as well as the stationary distribution exists as well as the limiting distribution exists, and both are going to be same. Now, I am going to give the conclusion. So, in this talk we have discussed some important results for the irreducible Markov chain. Then I have discussed what is the meaning of a limiting distribution, and I have given one example of how to compute the limiting state probabilities. Then I discussed the ergodicity. Then I have discussed the stationary distribution and how to compute the stationary distributions for a irreducible, a periodic, a positive recurrent, whether it is a finite state or infinite state Markov chain. I have given few examples, and I have given an example in which the stationary distribution exists, whereas the limiting distribution does not exist. And I have given some examples also. With this, I complete today's lecture. Thanks.